Hi, welcome back. We're in Lecture 9, Segment 2. The topic of Lecture 9 is the central limit theorem, which is a really important concept that underlies everything we've been talking about in the last few lectures, especially with respect to null hypothesis significance testing, obtaining p-values, and deciding whether something is statistically significant or not. In this last segment, I'll walk through the formal definition of the central limit theorem, and hopefully this will all come together so that you'll see how we get from, say, a regression coefficient to a t-value to a p-value to making that decision to reject or retain the null hypothesis. So let's look at the central limit theorem. Formally stated, it has three principles. So first, the mean of a sampling distribution is the same as the mean of the population. Second, the standard deviation of the sampling distribution is the square root of the variance of the sampling distribution. That's just saying standard deviation is the square root of variance. And finally, this is a very important piece, is the shape of a sampling distribution is approximately normal, either if we have sample sizes that are greater than or equal to about 30, or if the shape of the population distribution is normal. So note that if we have big enough samples, and some people might quibble with that n of 30, some people might make it a little higher, some people might make it a little lower, depends on the statistician you're talking to. But the point here is that the population itself doesn't have to be normally distributed. As long as we get multiple samples of large enough size, say n greater than 30, then the sampling distribution will take on a normal distribution. That's a critical point. So now let's put the central limit theorem together with NHST in the context of multiple regression. So this is what we did when we did the regression examples and what we do in lab when we do the regression examples. If we're doing NHST, then we start with this assumption that the null hypothesis is true, right? That's the game of NHST. You start with that assumption. You then conduct your study. You can then calculate your regression coefficient, B. You can calculate the standard error of that. And then you can calculate a t-value. And you saw that in the R output. And the t-value is simply the regression coefficient over the standard error. Conceptually, what the t-value is, and you'll see this throughout the course in null hypothesis significance tests, the t-value is essentially a ratio. It's a ratio of what we observed, the actual regression coefficient, the slope relating x to y, the slope that we observed relative to what we would expect just due to chance. So if I get a t-value of 1, then I didn't find much of anything at all. I know that's not going to be statistically significant. I know that p is not going to be less than 0.05 because what I've observed, my slope, is exactly what I would expect just due to chance. Typically, I want to get a t-value of at least 2 or more to show that I've observed a slope twice as large as what I would have expected just due to chance. But it's this conversion from the t-value to the p-value that we need to solidify in this last segment here. So each t-value has a corresponding p-value, but it depends on the sample size. So we start out with this assumption: if the null hypothesis is true, that would mean that in the population the slope is 0. Then no one sample should have a very high or very low slope. Let's say I obtained a very high slope. Therefore, I would reject the null hypothesis. What I want to do now is get more specific about this very low, very high. What exactly constitutes very low, very high? Well, it depends on this normal distribution. Remember that third principle from the central limit theorem. It states that a sampling distribution will take on a normal distribution, or it will approximate a normal distribution if we have sample sizes large enough, right? So if we get multiple samples and the sample size is large enough, then we'll approximate a normal distribution. That means I can make probability judgments about my outcome. Now, it didn't say in the central limit theorem, that third principle, it didn't say you get exactly a normal distribution. It says it approximates a normal distribution. So you don't get that actual perfect normal distribution. What you get instead is called a t-distribution. And there's actually what statisticians refer to as a family of t-distributions, depending on sample size. So if you have a really large sample, then your t-distribution that you can use for your probability judgments to obtain your p-values will look much like the perfect normal distribution. But as your sample size gets smaller, your t-distribution gets a little wider, which means you need a larger t-value to get out into the extremes to get a low p-value. But that's where the p-value comes from. We do our study, we calculate our regression coefficient, we calculate standard error, we calculate t. It's simply b over standard error. Then I have a certain t-value. Then based on my sample size, I pick a certain t-distribution, and I find where is that t-value in the t-distribution that I need to use. And if it's way out here in the extreme, then I'll obtain a low p-value, because the p-value says it's the probability of obtaining these data or more extreme, given the assumption that the null is true. Well, the null being true would give me a t of 0. So if I get an extreme score way out here, I'm going to get a low p-value, and I'll be able to reject the null hypothesis. So where does the p-value come from? It comes from the t-value and its corresponding t-distribution, which depends on sample size. And the p-value, to be specific, is just the area under the curve at that particular t-value and beyond. So if you're way out in the extremes, then you can have a low p-value, you'll reject the null. If you fall around the middle, then you'll have a high p-value, you'll retain the null. So to recap, we assume the null hypothesis is true, we conduct the study, calculate our statistics, get our t-value, and then we can get our p-value based on t and the sample size and the appropriate t-distribution. Again, if the null hypothesis is true, no one sample should have a very high, very low slope. I obtained a very high slope, therefore reject the null. Very high and very low simply means p less than 0.05. So less than 5% of the distribution in the extreme positive tail of the t-distribution or in the extreme negative tail of the t-distribution. Now remember, I want to reiterate at the end of this segment, I'm wrapping up here, sampling error, therefore standard error, is largely determined by sample size. Right? We went over this when we talked about sampling, way back when I introduced the notion of sampling error and defined standard error as the average amount of sampling error. Right? And this should just be conceptually easy to wrap your head around. If I have small samples relative to large populations, I'm going to have a large degree of sampling error. It's also right there in the math. So again, sampling error is largely determined by sample size. Back when we talked about sampling and the idea of sampling error, we illustrated this by showing you what the distributions look like for 6 different samples of different sizes. So the first one on the upper left is sample size of 10, then 20, then 50, then 100, then 200, then 1,000. And the thing to notice in these different samples, and this is what we covered when we talked about the idea of sampling error and standard error, is this smooth function here, this normal distribution, when sample size is only 10, is much, much wider than the function when we have a really large sample, say 1,000. That's because standard error is the standard deviation of this sampling distribution. And as samples get larger, they're going to squeeze in around the mean, and the standard error is going to get very low. This goes back to the problem of NHST being biased by n, right? That's like this example here. Let's take it even further. Imagine we had 1 million subjects in our sample. Then the standard error would get really, really small, and that distribution would get really, really tight. But remember, t equals b over standard error. If standard error gets so small, then it won't really matter what my slope is. I'll get a pretty high t-value, and a pretty high t-value will give me a low p-value, and I'll get something that's statistically significant. Okay? So it's important to try and obtain large samples to give yourself a chance to obtain a significant effect. But always remember that NHSTs in this whole process is biased by sample size, which is why I advocate following up NHSTs with estimates of effect size. Another way to look at this, and just to drive home this point, that sample size really drives and determines sampling error and influences the t-value and the p-value, is here, again, we've taken 6 different sample sizes, again, same sizes, 10, 20, 50, 100, 200, and 1,000. And we standardized each of these samples so that they would have a mean of 0. And then we just looked at the standard error associated with that mean. And the first thing to notice is in this first sample with an n of 10, the mean is plotted right here in this bar plot. It's not even 0 because there's such a large degree of sampling error, right? And this bar here reflects the amount of sampling error. That's the standard error bar. So what you see as sample size increases, the actual mean approximates 0, and the standard error bar shrinks because standard error shrinks as a function of sample size. Again, it's a critical point which is useful when you're designing experiments or studies if you can get large samples, but it can also be misleading when you obtain statistically significant results with really large samples. Again, that's why we follow up NHSTs with estimates of effect size. So to wrap up this segment and hopefully bring the last few lectures all together and wrap it up, the central limit theorem has these 3 principles. The mean of the sampling distribution is the same as the mean of the population, and if we're assuming the null hypothesis to be true, that mean's going to be 0. The standard deviation is just the square root of the variance. And then third, most importantly, is that the shape will approximate a normal distribution if we have large enough samples. Even if the shape of the population isn't normal, the shape of the sampling distribution will approximate that normal distribution. It won't get perfectly normal, and we'll get a family of t-distributions instead that depend on sample size.